Okay. Do you see my presentation? Yeah. Okay.
Yes.
Thank you so much. Okay. Let me see. Okay. Okay. Thank you very much for accept all the speaker start here and show these results that are very important for our work. And then we start to talk about a little the non-equilibrium theory of arrested spinodal decomposition. In this work, we try to understand a little more what is the process when we found arrested state inside of the spinodal line. Okay, first I give a little about the motivation, and then I will apply the theory that in the groups of Magdaleno works, and say how we can obtain the non-equilibrium phase diagram and some structural and dynamic properties. And then I will conclude with some summarize of this work and what was the more important points of this work. Okay. In the case of the in the case of how we try to connect all the information that in many groups have, especially when we have experimental or simulation results, is so important because if we try to connect all these topics with some theory, it's a little hard to get all this topic in only one theory. We need to figure out how to get, for example, the phase diagram and maybe some visualization, and how we can get some dynamic properties or rheological properties and connect all this information to get or to characterize this type of system that present one spinodal line. Also, to get all this information inside of this region is very important because for thermodynamic, equilibrium thermodynamic, we can see that inside of this region, we can find only phase separation. But when experimentalists or some simulation do prepare the system in some point and at equilibrium, and then they do a quench inside of the region, they found some different structure that the phase separation. In fact, there are so many works that try to see how is the evolve of this structure as a function of the waiting time, and also put all the information like the dynamics or rheological properties also as a function of this waiting time. Okay, this is another example that we can see how people try to connect the spinodal and the experiment and get some parameters that try to describe this type of phenomenon. However, the theory is not presented because it's a little hard to get all this information in non-equilibrium systems. Okay. Then what is the purpose of this talk? Well, like all the theoretical person that work in this field, which is to get one non-equilibrium statistical thermodynamics that permit us to get structural properties or phase diagrams or equation of the state. If we give some information about of our system, like the interaction potential between the particles, and plus what is the protocol that we can use to make this type of systems. In this sense, like in the previous session that has been presented here, in this work, we use the non-equilibrium self-consistent generalized Langevin equation that, in a sense, one of the most important results is that we have one equation for the static structure factor, and this equation provides the evolution of this property as a function of the waiting time. This equation has the characteristic of give us two types of stationary states. The first one is when we have equilibrium states, that this means that this part is equal to 0. But the other stationary state that this theory provides is when the system is in some rested state. This means that this guy that is here start to go to 0, and then this means that the system will be in some arrested state. Okay. To check this theory, in this case, we use the most simple case to understand what happened if we prepare our system in some equilibrium state, and then we quench inside of this spinodal region and see what happened with the prediction of this theory. This is the most simple case because this system is very easy to manage because only have two control parameters. One could be with the temperature that also models the attraction between the particles, and the other is given by the density of the system. Then that we can do in this theoretical job is to prepare our system and do several quench inside of the spinodal region to different volume fraction. Then we can move the temperature, and also we can move the volume fraction. Okay, the first thing that this theory provides is the non-equilibrium phase diagram. The most important thing of this result that gives this theory is that, we provide some theoretical information and what is our protocol, that in this case are quenches inside of the spinodal region. And then we use the theory and provide this type of phase diagram. Then the result is that this theory says that we can find inside of the spinodal region 3 types of phases. One is the full separation. The other is that if we do a more deeper quench, we can find one region of gel. And the other important thing is that the glass transition that is given by high densities, this line enter to the spinodal region and continues inside of this spinodal line to very high temperatures. This means that to see this effect, we need to have a very high or very strong attraction between the particles. Okay. This was the first result that we found is important because in many theoretical experimental framework and also simulation, they try to draw what is the phase diagram when people do a quench or try to get the information inside of the spinodal region. And also they say the same information that we get in using this theory. One is that to very near to the spinodal line, we can find phase separation, but if we do more deeper quenches, we can find gels, or even more, we can find like these porous glasses. Okay. The other properties that this theory provides is also the dynamics of some properties and also the rheological properties. And we, in this talk, we try to analyze what happened with this type or properties. Okay. Like a cartoon, and for no use all this equation, we can discuss later if you want. This theory works like this. Okay, also, well, we need to provide the information and put this information in this theory. This theory, one of the most important equation is the static structure factor. If we have this static structure factor as a function of the waiting time, then we can obtain all the dynamic and rheological and statical properties, and then also the mobility of the particles. And when we have this mobility of the particles, we put this information inside of this equation, and then we resolve this equation and get the next static structure factor, and this do in a circle, and then we have all the information of the system. In the case of the static structure factor, we see the next information. Okay. We see that if we do a quench, in this case at the volume fraction phi 0.1, we can see that this static structure factor starts to evolve in this manner, and then start to appear one like a mountain in a very low peak. And this means that the particles start to aggregate, and then this growing in this property means that the particles start to get each other and start to do aggregates. And well, also in this case, we perform some simulation, and this is the comparison between the simulation and the theoretical prediction. Okay. Also, we try to compare with another experiments and see if the theory predicts some important behaviors. And for example, in this paper, they do also a quench inside of the spinodal region. And they see also that in the case of the static structure factor, this also appear this behavior low Q peaks. And if they integrate the area of this property for each static structure factor and define this quantity like this first moment, and plot for each static structure factor this quantity as a function of the waiting time, they see this type of behavior in this quantity, and they claim that the behavior of this property has this power law. Well, in this case, using the theory, we did the same exercise that they do in the experiment, and also we found the same power law that they found. And well, in this case, also we can plot this information to different quenches at different temperatures at them, and we can see that this information looks like this. Okay. Also, one important thing that we can see in this type of phenomenology is the mean square displacement. And analyzing how is the behavior of the mean square displacement, we can see that if we quench above of this line, this glass line to very low temperature, we can see that the mean square displacement predict these two steps. These two steps are characteristic of the gel transition, and this is one important thing that we can see, because this means how is the cage of this gel forming, and is related with this information. But in the case, if we do a quench more deeper, that in below of the dashed line, we can see that the behavior of the mean square displacement look like this. Like is the discussion that start to follow in the second talk, that it was very, very nice to see. Okay, in the case of this second step in the mean square displacement, have been reported by this in this group that try to figure out what is the competition between the gel and the glass faces. Okay. Another important thing in this work is the rheological properties, because theoretically we can develop one equation to get the viscosity of the system. Then if we work with if we relate the viscosity with the stress tensor and work in non-equilibrium system, we can found one expression to relate the properties that this theory can provide and with these rheological properties. This is important because when we do this, we also can obtain the G prime and GB prime using these expressions. That one goal of this theory is see if this expression can to predict some experiment results or simulation results. In this sense, for the theory, is to prove this theory, we put this challenge in this work. They plot some rheological properties when they do a quench inside this region. For this system is given by some spinodal line. And they plot what is the rheological properties and also they claim that they see some property that, namely the latency period. This means that this latency period is the time that when the system start to see, when the experiment start to see, when this quantity G prime start to grow very fast, then if they need to wait, they prepare the system and then need to wait some time, that this is the latency time. And when they start to see that this property starts to grow very fast, this is the latency period. They do this exercise to different times and plot this information in this sense. Okay, if they collect all this information and plot this time as a function of one quantity that they name S, that is defined like the temperature minus the temperature of the spinodal, between the temperature of the spinodal, then they see that this latency time has this behavior, and they say that this time has a slope that is equal to 2.5. Okay, then what happened with the theory? In this sense, we, in this slide, I present how looks the effect of the G prime and G B prime as a function of the waiting time to different frequency, as a function of the different frequency for different waiting time. And we can see that this information start, this is this part start to one value. And then when the time is start to evolve, the evolution of this quantity start to evolve like this direction, and also the G prime. Okay. Then, if we put or if we fix the frequency and we collect all these points, we can obtain G prime as a function, G prime only for one frequency as a function of the waiting time. When we plot this information in this sense, we can see that the behavior of this quantity is something like this. Okay, this is only for one quench. Then we need to do the same exercise to different quench. And if we do that, we can see that the behavior of the G prime looks like this. And also we can collect all this information about the latency time. And if we do this, the behavior of this latency time look like this. Then comparing with the experimental results, we can see that the theory predict the same behavior like the experiment, and also predict the same behavior of the latency time. Also, if we put together the experiment and the theoretical predict, we can see that both systems have the same slope. Okay, but okay, this was only the first challenge that we see using this theory. But also we can obtain the zero frequency viscosity, and here I show what happened when we see this behavior. If we do a quench to very high concentration, we can see that in this case we go to one equilibrium state to another, and we perform a different quench, and then we can see how the viscosity evolves as a function of the waiting time. Then when we do a quench in this region, we can see that the system starts at some viscosity, and then this starts to increasing, and then after some time, this parameter start to be a constant. Like we are closing to this glass transition, we can see that we need to wait more time to see this equilibrium state. But what happened when we cross this this line? We can see that the viscosity start to increase, and then this continue increasing as a function of the waiting time. One interesting thing is see what happened in this region. Okay. Doing the same exercise, we can see that if we do the one equilibrium state to another, we can see that the viscosity look like this. And if we perform quenches inside of the spinodal line, this viscosity look like this. And we can see that if these quenches are more deeper, this latency time start to be more shorter than when we do a quench very near to the spinodal line. And when we cross this line, also we observe the same behavior like the two very high concentrations. Okay, this is the behavior when we have a low volume fraction, and this is the behavior when we have high concentrations. Okay, but well, and also we can see that in this viscosity also predict that in some way the viscosity start to be like a pseudo equilibrium and then start to grow at some time. This behavior also was previously seen in the mobility of the particles. And then we see first this behavior in this property than the viscosity, because the rheological properties was developed after we try to understand this phenomenology in another properties. Okay, another important thing is that also this theory provide in some way how looks the evolution of the density as a function of the time. And this is one example when we do a quench very near to the spinodal line. And if we do a quench more deeper, this is the example, and more deeper, this is the example, and this is to very high volume fraction. Then we can see that at the first step, the system tried to separate into phases. But when we do a quench more deeper, the stage start to separate more lower as a function of the time. Okay, like some conclusion, now we have linear viscosity properties as a function of the waiting time, and I think these properties help us to understand a little bit more about the gel transition during this arrested spinodal decomposition, and also try to connect all these properties to another that maybe are confused because when you only have one theory to try to imagine what happened if the systems go to this type of phenomenology. Also these rheological properties help us to identify the latency properties that at the beginning was only a guess, and now we are sure that this phenomenology can see in experiment and also in simulation. Okay, and this is the work group that helped me to develop this nice work, and also the acknowledgement to develop this this work. Okay, and thank you for your attention. And okay, I think and thank you for the others participants that their talks helped me to understand a little more about this type of phenomenology. Okay.
Thank you very much, Leticia. It was a very interesting presentation. Is there any question from the audience? I think there's one, Hector Manuel Lopez, or perhaps it's just clapping. Now I'm more aware of it. But there is Mathias, please, Mathias.
Yeah, thanks for the nice talk. I was wondering, in your expression for the viscosity, the H, T entered in two places, one via the structure, yeah, precisely here, one via the structure factor, S of K and T, and then also via the H dependence of the density correlation function, F of K, O and T.
Yeah.
Can you tell a little bit on where the first part is important, where the second entrance of T is important, or how one can disentangle those two places of the H entering the viscosity?
Okay. In this case, we try to develop this expression, the microscopic, the stress tensor, and we try to develop like MCT did in the past, but now with non-equilibrium conditions, and we obtain, I think it's look like the same condition, only that the assumption that we get, that we assume to get this expression are so different to connect this expression to the static structure factor and the correlation function. Okay, I think the derivation is a little complicated, but we can discuss if you want. Yeah.
Okay. Yep. Thanks.
I think Thomas Gibaud has also a question. Thomas, please.
Hey, thank you for this nice presentation. I had a question concerning the structures that you get. So you get something very similar to Peter's result, and in general, depletion gels. That is to say that you have kind of clusters that are, or a peak that represent a few tens of a particle. The strand of your network is about tens of particles. And as I remember, that's very different from the case of smaller colloids or proteins, where the strands are very thick. They're about 1,000 particles, and the structure that you get is more alike of a spinodal, where you have a very long and broad porous regime that tells you that the interface between the fluid and the gas phase and the dense phase is very sharp. And can you explain this kind of difference from your simulation point of view, or where do you think this difference comes from?
Okay. In this case, well, in the case of the job of the Peter Lu, he shows the two sketches. One is for depletion. Yeah. Well, let me see. In this sense, like we try to do, well, they put the phase diagram and they do a quench inside of some spinodal region, and also to compare. In this case, also we try to compare only in the case of they have gelation. No, I don't remember the other type of system that they have.
So the system they have, it's colloids plus polymer, and the polymer creates a depletion. So they don't really, they can't really, I mean, they can't do a continuous quench from a fluid state to, they just meet their system and they go very fast to the microscope. And thanks to the slow dynamics of the colloid, you can see basically the colloid move and form their gel.
Yeah. Oh yeah.
And as you see on the structure they get, you see the peak here is basically is not very far from the particle size, meaning that the peak, which represents the correlation length on your system, is about, you know, about 10, 20 particle in size.
Okay.
And that's compared to smaller particle and protein systems, that's very small. In protein systems, the peak is about 1,000 particles in size. So it's a very different structure, actually. I was wondering if you had an understanding of what's the difference, why there is so much of a structural difference between these two kinds of arrested phase separation.
I think the difference is that in this system, the position of the low peak move more faster than in the case of our system, for example. This is one difference that we have. But for example, we can see that this theory predict the similar ideas. For this reason, we know map each other the system between we have and the experimental phase. This is
this is very convincing.
Yeah, but okay. In this sense, we understand that this phenomenology is very similar when we have some spinodal region. But also we need to look, for example, when the attraction are, because this is like a Lennard-Jones system. Mm-hmm. And also we need to provide what happened when we have short interaction. In this sense, also maybe we provide more information about this type of system. This is only the first step to try to understand this type of system, but also our wish is to compare with the experiment, that the experiments say that the interaction are more shorter than we have here. Yeah.
Okay. Magdaleno raised his hand. Please, Magdaleno, would you like to contribute?
Yeah, thank you. I'd like to mention with respect to Thomas' question, that's a really nice point that you noticed. And excuse me, when we try to compare with systems with very much smaller particles, then it's exactly what you said. In those cases, we are using a model that is to represent mostly systems that let's say we're doing an instantaneous quench inside the spinodal line. And for a big colloidal particles, like Peter Luce and this group's system, that is a little bit better approximation, so to say. Within the real experimental times, that is closer to an instantaneous quench. You prepare the system, as you said, put the polymer, and that almost immediately you have the system evolving, and that's a good approximation. That's why in this figure that we have in front of us, there is no need to make rescalings or anything like that. Now, when we go to systems of, let's say, proteins or something like that, then the behavior is qualitatively the same, but we have to, in order to compare, we have to rescale, as you said, from 1,000 particles to 1 particle or something like that. And the reason we believe that the theory could model that, because in the case of a smaller particle, then experimentally, when you do the quench, probably an instantaneous quench is not a good approximation. And then you have to do a finite rate, finite cooling, sort of cooling rate to go to the final point. And that leaves you a lot of time for you to sample the region where the heterogeneities grow very quickly and too fast. And that's why they can group too many particles in these heterogeneities. Whereas if you do a similar quench for much bigger particles that take longer to do that, then the picture predicted by the instantaneous quench is better. But these are, let's say, guesses that we have. We would like to test that. And it would be nice to do experiments, by the way, to really revisit these experiments.
I'm very happy to hear you. To hear this opinion, because I believe I have the same. It took me a while to understand why there is a difference, and I think you're right. It's when you do protein, you go through the phase separation, but since everything is small, you really grab the phase separation and you get the structure from the phase separation before arriving to the arrested state. That gives a very different structure from what Peter Luce do. Because everything is slow, you go so fast through the phase separation, you don't really see it. It's like basically you do this fractal aggregation rather than arrested phase separation, kind of.
Yeah.
And yeah, I don't know if there is any in-between system experimentally to test this idea, actually. That's a good point, because in protein, you can do it as fast as you want, but you always get the phase separation. And I was never able to get a kind of Peter Luce structure. So yeah, maybe something intermediate in size, I don't know. It's a good, I think there is some nice science in-between science to do between large colloid and small proteins.
Yeah. Yeah, thank you. Luis, can I also make a comment with respect to Mathias Schmidt?
Of course.
You asked, let's say, in which channel, let's say, the waiting time influences more, either from the structure factor or from the dynamic structure factor, dynamic correlation. I just wanted to say that we don't know, because we get this expression. What is interesting is that this is exactly the same expression that people have derived for equilibrium within MCT derivations like Gerhard Megele and so on. And what is amazing is that really you can go through basically the same derivation, but never use the canonical or any equilibrium ensemble. This is completely independent of the ensemble. So that means that within how to say, assumptions regarding homogeneity and this kind of isotropy and symmetry properties, then the derivation goes through perfectly with independence of the specific ensemble employed to make the average. And this is something which is interesting because we see that with many other properties, the energy, the pressure, and so on. And so we can carry many expressions that we normally use for equilibrium happen to be perfectly valid away from equilibrium, at least as long as you have a homogeneous, isotropic, and so on. It will not, I don't know how to do it in the case that you do really beautifully when you apply shear or external fields. And that would be, my point is, that would be a nice thing that I would love to discuss further with you and the people interested on that. Thank you.
If I understood correctly, also Mathias' question was regarding the difference between the two times appearing in such equation, right?
I don't think so.
No, I think it was the question, isn't it?
Well, can I comment? So Magdaleno
Yeah,
addressed the point of where the two channels that you had, what is the importance of the one channel to the other? So how the structure changes and how the time-dependent correlation function changes. And this is really, I would say, comes out nicely by the approach that you have these two channels, and it would be interesting to know which is more important. And in a way, you know what you just said about the approach being independent on the equilibrium canonical averaging that's necessary. In a way, this we generalized with the ITT approach also. We, for simplicity, kept the equilibrium averaging in order to only concentrate on the dynamical phenomena. So there are, I would say, in the nonlinear response approach, there are various ways of where to put the nonlinearity, either in dependence or in the, say, the initial distribution function that you integrate up. And yes, there are interesting connections, and it would be interesting to explore them and to find out more there. Yeah, I agree. It would be nice.
Mm-hmm. In any case, just to clarify, because Luis is mute now.
Oh, sorry.
But Luis, you were saying that probably Mathias referred to the presence of two times the correlation.
That's what I
time.
understood as the two channels for the relaxation, right?
Just to make things clear, I think that Mathias referred only to the waiting time. Of course, the correlation time appears in F, and it doesn't appear in the static structure factor, in the structure factor.
But indeed, the correlation time, and especially the structural correlation time, it is somehow bonded within this model to the waiting time, right? Which means, I mean, you have this tau that appears on F, and which in principle, if you fix, for instance, the tau alpha relaxation time of your non-equilibrium intermediate scattering function, it evolves with time. And it is this machine which, let's say, more or less bonds or links both times, because the alpha relaxation times grows with waiting time, let's say during a transient time or whatever. This is what gives you the two channels, the connection between the two channels, no? And that connection, it is established, let's say, in equations that give the evolution as a function of tau and t at the level of the dynamics through the dependence of the waiting time of the static structure factor. So in another way to say it is you have a master equation for the static structure factor, which depends on a local mobility, and that mobility is coupled to the to equations which involve the tau evolution of your intermediate scattering function. And all this thing, it is put in that equation, let's say, when you solve it at the level of the viscosity or any other, let's say, a structural or dynamical property. We might discuss that more in detail with equations in front of us, probably, Mathias, if you would like to discuss further. I mean, not today, of course, but soon enough.
Can I add a question there in that context?
Yes,
have
of
you
course.
also at, say, oscillatory changes? So the protocol that you had here was turning on the, changing the state. This is, of course, say a simple time-dependent protocol. You just change the state, but you could also envision doing an oscillatory change. Have you explored this already, and do you know what you would expect there?
No, in this case, we can explore this type of systems, phenomenology. No, only in the case of the linear response. Mm-hmm.
Yeah, may I add? What Leticia talked about was the simplest exercise, which is assuming homogeneity, isotropy, and all this. And you do the quench and then let the system alone. But the next thing is to use the analog of linear response theory that we have not developed and applied. And that should be the next step in the application of the theory, to apply, let's say, oscillatory or any other. Let's start with a small external perturbation, so to say. That's why I say we would love to have the advice of you guys and in general as to how we can get into this field, because it is actually new to us. But we think that the equations that we have, if extended to include those effects, would probably be an interesting exercise. We would like to do that, but we have not yet done that.
Okay, I think there was a remaining question from Jörg, but probably he's not here any longer. He said he wanted to ask something to Mathias at the end, but I don't see him in the list of participants any longer. So is there any other question from the audience? Well, apparently not. So in that case, I will first, Mathias, do you want to comment something?
No, in a way, I just wanted to say thank you for putting this program together, and the suggestion of that to stay in contact about the development of these theories for nonlinear response. That's certainly very interesting for me also. Yeah, I'd love to stay in contact. So let's just see how things evolve and then discuss this. And
as George pointed out, I mean, COVID gave us that in a positive way, no? Give us the realization that we can just work in this format like easily and propose things and without having to move to Germany, or you coming here to Germany. And I would say that regarding your comment, I think that the best way to do it, to make it happen, that like to try to include in all way of describing, let's say, these properties, these rheological properties of matter close to non-equilibrium conditions will be to having the support of Thomas Voigtman, since he is like more or less now somehow an expert also in the Langevin approach. I think he's the chosen one to lead us to how to adapt from one theory to the other, let's say one or other way to approach things. But I'm convinced that the more we look at it, the more I'm convinced that these are just two different ways to express the same physical laws, or up to a very good approximation, let's say. And probably we can see how to adapt. I mean, the formal derivation, it's always tricky or demanding whatsoever. But at the end, when you look at the equations that you derive, when you look at the structure, when you can more or less infer how to adapt from one way to the other. And for instance, in the case of MCT, once you formulate the Langevin approach in the vertex function way of expressing the theory, you immediately recognize, okay, this is a simpler theory because you can contract this index here for the case of mixtures, for instance, and so on. But in essence, it is the same. So if you have already your MCT equations, then at least you know where you should put your Langevin equations, at which level, let's say, and even put an answer, guessing or whatever, and try, and then you can more or less handle the formal derivation. But this is a strong, let's say, hint when you know what do you have to derive. So I will, and I think I'm speaking in the name or on behalf of the whole group, but we will love to stay in contact, Mathias, for such kind of derivations. So we will contact you soon enough. And Thomas, George, is there anything that you would like to contribute for the end of the session?
Well, actually, I must say that I'm sorry, actually, that I could not follow the last two talks. So I got some shocking news that I think I should pass on to you guys. So you might know a brilliant colleague of us, Jim Swan, MIT. So I just heard that he just passed away this morning. So I'm really sorry I could not participate. So maybe some of you really knew Jim. He was a student of John Brady. Anyway, I would like just to thank you guys that you organized this. And I believe that we should stay in contact anyway. And I'm sorry for the sadness.
Yeah. Too sad. Mm-hmm.
Thomas, if you want to say a final word?
Yeah. So that's a very sad news, of course, and okay, just to come back to the subject of the conference. No, I was very happy to participate to this conference, and it was very pleasant, and I like this kind of small audience conference where you can easily exchange and participate to the debate. So thank you very much. I really appreciate this format. And also, I like it that it's in a Zoom way, because I probably wouldn't have made it if it were in Mexico. But so, yeah. Thank you.
Okay, well, I'm happy that you found it so easy and nice, and I think there is a clear opportunity for defining let's say possible collaboration projects, as you were just discussing with Magdalena, but we will contact you also soon enough. And I will also like to read this message from Diego Chamel, which says, many thanks for organizing this very stimulating symposium. Keep me in the loop if you continue with these events. Many thanks for this very stimulating session, and greetings to all friends I have not seen for a while. So if there is any other question or contribution, I think it is then time to conclude our final session. And I will also like to thank to all the organizing committee because of the enormous amount of work to make it possible. I mean, even though it is Zoom and so on, it requires a lot of organization to more or less bring this event together. So if there is any other comment from you, Magdaleno, perhaps you want to say something?
I just wanted to thank the organizers and particularly the speakers that got along with us of organizing this in a very short call and for their great talks. It was a very pleasant session. Thank you very much. And thank you, Luis, and the organizers.
Okay, well, then I will make a virtual applause in the name of the event. And again, thank you very much to everyone, and we will keep in contact, be sure of that. And okay, then stay healthy and many greetings to everyone. Felipe, hi.
Bye. All the best.
Bye,
Thank you very much.
Bye.
Bye.
Bye, everyone.
Ciao.